A surface integral is a generalization of multiple integrals to integration over surfaces. Any integral which can be evaluated over a surface is called as surface integral. Now, there are a lot of applications and physical interpretations of surface integrals. If the vector function represents a velocity of a fluid, surface integral gives the flux across the surface S. Now, in electromagnetic theory, it may give the corresponding flux. So, the working rule to evaluate the surface integrals are as follows. Assuming that this is not a flat surface, say phi is a given surface, find the unit normal to the surface, compute scalar product of f with n cap, then the surface is projected onto one of the coordinate planes, maybe the xy plane, where the projection, the small area element, surface area element would be something like tx dy, n dot k is the unit vector to the z-axis. Similarly, the projection for yz and xz plane can be obtained. We have the following expression. So if we have to evaluate a surface integral, this should be projected onto, say, one of the coordinate planes, and then this is a multiple integral to be evaluated over a given region of the projection. We'll just discuss a few examples over here to evaluate the, say I have an example here, evaluate surface integrals. A vector function is defined like this. This is a part of a plane located in the positive octant. Now if we just try to write this given equation, the surface, you have a plane in the intercept form, taking this as the surface, computing the gradient. Remember, gradient is a vector quantity given by the following expression. The outward unit normal represents the following vector n cap given by grad phi by its magnitude. Getting this normal to the given surface, computing the scalar product yields a expression of the following expression. Now projecting the surface onto xy plane, we have a sort of a triangular region given by the following expression. Remember, on the xy plane z is 0, the projection of the positive octant of this surface leads to a triangular region in the xy plane. So this is the formula to evaluate the surface integration. So eliminating z from the plane equation, we can compute the integrand, which turns out to be something like 36y minus 12xy. Taking the projection of the surface onto the xy plane, we have this area element followed by, there is a n dot k, which is 6 by 7. We insert everything in the expression. Once this part is completed, we just try to evaluate the multiple integration over a triangular region, which gives us the following value there. Note that once the projection is taken and the z is eliminated from the given problem, it is essentially the same double integration. So that's the reason we call this as a generalization of the double integrals. Remember, double integrals has been discussed in the first semester classes, so it is the same expression. Computing this, integrating with respect to y holding x as constant, then integrating with respect to x between the appropriate limits gives the following value. Now, there is a similar example over here. Note that this is a flat surface over here. See, z equals 4. So in this type of situation, generally we cannot project this surface onto xy plane. So the projection onto any other coordinate plane is taken over here. So the surface is actually projected on the xz plane, and a similar computation is done. So that leads to the following expression. Generally, when you have a flat surface, we have something like a z constant there. So such surfaces cannot be projected onto xy. It has to be projected on some other coordinate plane, and then the respective expression needs to be used. Here we have taken a projection onto xz plane, and then the integrand is computed in a similar manner to the previous example there. Now there is a very important result pertaining to the line integration and the surface integral, which is supposed to be referred to as the Stokes theorem. Now the Stokes theorem is supposed to be like a generalization of the Green's theorem to the higher dimension. So Stokes theorem has interesting applications. Now Stokes theorem is supposed to be the relation between the line integration and the surface integral given by the following expression. If you take a two-dimensional type of situation, it just reduces to the Green's theorem. So to illustrate the result, I have just one example over here. So I have just taken a simple problem over here. Verify Stokes theorem on the upper half of a surface, which is a unit sphere centered at origin and radius 1, and something like a hemisphere type of a situation where the boundary is a circle over here. So whenever you are asked to do the verification, there are two things required over here. One is the line integral part, and the other one is the surface integral part. So the line integral part is relatively easy to handle over here. Substituting for f and this dr leads to an integrand expression in the following format. In the xy plane, there is no z, so dz becomes 0. So just rewriting this and using the parametric equations of a circle leads to the following line integral, which has an answer as something like pi. Coming to the right hand side, we need to compute this vector curl. Computing the curl followed by rearranging this and substituting in the right hand side of the Stokes theorem. Here, note that this integrand reduced to 1. And when you just look into the hemisphere projected onto xy plane, it's something like a circular region we would get. So it's precisely area of a circle with center, origin and radius 1. So this gives pi. So note that they're essentially same. The big usage of the Stokes theorem is something like, line integral would represent work done by force and things like that. So when the surface is like a bit hard to evaluate with the usual method, converting into the surface integral, sometimes curl of the surface integral helps us to sort out the example there. So there's a similar example over here where there was something like evaluate using Stokes theorem the following integral, line integral, where we have a boundary of a triangle. Now if you just look into the conversion and things like that, the problem of line integral gets simply reduced to finding an area of a triangle over here. So essentially when you compute the curl, it becomes a constant vector. The right hand side simply reduces to finding the area of a triangle, which is half base into altitude, so you get height 1 by 2. So